If you were to extract all the salt dissolved in the global ocean and spread it evenly across all of Earth's land masses, you would be left with a solid block over 500 feet thick. That is the equivalent of a 40-story office building covering every inch of every continent. This raises a foundational question. How did this much mineral material end up in the water? The standard explanation begins in the atmosphere. Rainwater absorbs carbon dioxide, forming a weak acid that chemically erodes the land, dissolving rocks into ions. Rivers and surface runoff then carry those dissolved minerals into the sea. When the water eventually evaporates, the heavy salts stay behind. This linear accumulation model frames the ocean as a passive reservoir for the continent's leftover minerals. But the math doesn't hold up. This river runoff process has been occurring continuously for roughly 4 billion years. On top of that, deep-sea hydrothermal vents and undersea volcanoes constantly leach minerals from the Earth's crust, pumping them directly into the water column. If rivers and vents have been dumping salt into the sea for billions of years, average salinity should be climbing, yet it remains capped at 35 parts per thousand. Under an additive model, the ocean would have turned into a solid salt block eons ago. There is clearly a missing half to this equation. Every drop of seawater functions as a high-turnover chemical transit hub. This is measured using residence time, an element's lifespan before it's actively removed. Iron, lower left, has a rapid 50-year removal rate, consumed by marine life. Conversely, sodium lingers for 68 million years, mixing uniformly to satisfy Marset's principle. Because every element has a mathematical expiration date, the ocean must possess massive hidden sinks that actively strip billions of tons of salt from the water. The biological sink involves marine organisms extracting calcium and carbonates to build shells, which eventually settle and compress into limestone on the seafloor. Hydrothermal vents also act as a filter. As seawater is pulled into the hot crust, chemical reactions strip out magnesium and sulfates before the fluid is ejected back into the sea. The most extreme geological sink is the evaporite basin. Tectonic movements can isolate entire shallow seas, causing them to dry up. This process locks away thousands of cubic kilometers of solid minerals deep into the Earth's crust over geological timeframes. The ocean operates as a self-regulating machine, where the rate of minerals entering from the land is matched by the rate of minerals being buried in the crust. Disruption of this delicate input-output balance can have catastrophic planetary consequences. 6 million years ago, a geological event called the Mycenium salinity crisis broke the system. Tectonic plate shifts squeezed the Strait of Gibraltar shut, severing the Mediterranean's connection to the Atlantic. As the basin evaporated, it transformed into a salt giant. You can see the progression in these 4 panels as the water level dropped and the basin became landlocked. This single event extracted approximately 10% of the entire global ocean's dissolved evaporate ions. This massive salt removal stripped so much calcium from the global ocean that it disrupted the carbon cycle. Without enough calcium to form limestone shells, the ocean's pH rose, which allowed the water to absorb more CO2 from the air, causing atmospheric carbon levels to drop and triggering global cooling. The Mediterranean eventually refilled, and the global ocean returned to its steady-state equilibrium. Modern salinity levels represent the current momentum of an active, moving river of dissolved rock. Tasting the salt in seawater provides a snapshot of mountains dissolving, vents erupting, and the Earth's crust rebuilding itself. This planetary balancing act is a continuous chemical cycle that makes life on Earth possible.